Okay, so your first exam was due last night, so hopefully everybody, I checked, I think pretty much everybody had already submitted it. So I'll later in the week I'll post solutions and the grading breakdown for the first exam, so that you can see that in a nice organized way. So as I mentioned yesterday, I'm going to proceed through chapter 6. So I'll finish most of chapter 6 today. I still have a couple of things that I'll have to finish up tomorrow. Well, mostly just Chinese remainder theorem is all I should have to finish tomorrow, and then we'll be moving on. But so first, as mentioned previously, exponentiation, yes. Okay. So I mentioned yesterday that one of the more important things to note about congruences is that computing these sorts of things, that is, computing some power, so some exponentiated thing here, mod m, is important, and it's also easy. It's easier than computing this normally, or I should say, it's easier to manage than you might expect. Of course, I should say, if you can, one way of dealing with this, it might seem a little weird that that's the case, because if you thought going forward, this definitely does not seem to be the case, just due to if you're doing the absolute brute force, like stupidest thing, you would exponentiate this thing, and then you would just brute force what this thing is congruent to, mod m, by just dividing it repeatedly by m, right? So there's a example that's given, which is say that you wanted to compute 3 to the 385 mod 479. Okay, so 3 to the 385 mod 479. Okay, so you might look at that thing and say, well, the stupidest thing to do would be to actually do this exponentiation and then look at it mod 479 by dividing it repeatedly by 479. That's clearly not what I'm going to do. So dealing with this, the one method that I'm going to show for dealing with large exponents, incongruences, is a method that relies on squaring these things repeatedly and then looking at this list of squares. So I'm going to square them repeatedly and then reduce them mod 479, and then use that to come up with a reasonable result. So the idea, square 3 repeatedly, reduce mod 479, and keep track of 3 to the 2 to the k, we'll say. Okay, this might seem a little strange at first. So first of all, note 3 squared is, of course, congruent to 9 mod 479. I mean, it's just equal. 3 squared is 9, and mod 479, there's nothing else to say there. So then 3 to the 4th is really 3 squared squared, so that's 9 squared. And so this is 81 mod 479. Everything I say here is going to be mod 479. I'm not going to copy that a bunch. So, and I'll do this for congruences from now on. Basically, when it's understood what these congruences are modulo, that is with respect to the modulus, when it's understood what the modulus is I'm talking about, I'll suppress it so that I don't just have to keep copying this. Of course, if I do something that is a change of modulus by, say, dividing in a way, where I'm dividing by something that's not relatively prime to the modulus, then that changes the modulus. Obviously, I would have to keep track of that, or else it's going to be, it's going to be a real mess to unpack. So, continuing this, I want to keep squaring here. So, next in the line is 3 to the 4th squared, which is 3 to the 8th. So 3 to the 8th, that's 81 squared. Right. So I just take my previous result. That's 81 squared. 81 squared is 6,561. And now I get something that's actually, I can reduce mod 479 to not just what I have here. So I can reduce this mod 479. Turns out that this is congruent to 334. Okay. So continuing, I look at 3 to the 16. That's congruent to 334 squared. Okay, so 334 squared, if you compute this, this is 111,556. Okay. So then reducing that mod 479, I get 428. Okay. All right. So I just keep going. So square again. This is 3 to the 32nd. So that's 428 squared. 428 squared is 183,184. 183, 184. And mod 479, this is 206. Okay. Continuing 3 to the 64. Well, that's 206 squared. So that is congruent to 284 if I go through this process. So similarly, shortening this, 3 to the 128 is 284 squared. That turns out to be 184. Okay. And then lastly, 3 to the 256 is congruent to 184 squared, which is 326 mod 479. So what am I doing, and how do I know when to stop? Okay. So to see what it is that I'm doing, to see what it is I hope to accomplish by doing this, now note that my exponent, I'm off, my exponent's off camera now, there we go. So note that 385 can be expressed as 256 plus 128 here plus 1. So this is actually related to something that was noticed. It was a non-standard algorithm, right, if you like, for multiplying. So it's actually the subject of what I think, at least as of 10 years ago, it was the oldest like mathematical wouldn't call it a textbook, I guess like a treatment or a mathematical article, if you like, was scribbled down on some Egyptian papyrus, like 4,000 or maybe like, yeah, something like 4,000 years ago, which essentially detailed this, not this exact method, but a method for multiplying two numbers through doubling. So you might have seen this trick before where you just, start with number double, 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 because doubling's easy. And then note that the thing that you're multiplying the number by could be expressed as a bunch of powers of 2. What did I really do here? What is this? Note further, this is just the base 2 expansion of 385. Of course, base 2, this is binary, right? So this is, i.e., 385's binary expansion. Now you might say, wait, where's all the ones and zeros? I just didn't write them out, right? So the point is that I just didn't actually express all of the zeros. I left those out. This is clearly the ones place, and then if I count up, right, I'd have 2 to the first, 2 to the second, that's 4, 2 to the, so I'd have 2 to the 2 to the third, that's 8, 2 to the fourth is 16, 2 to the fifth is 32, still none of those, 2 to the sixth is 64, 2 to the seventh is 128, so this is the 2 to the seventh place, right? And 2 to the eighth is 256, this would be the 2 to the eighth place, so its expansion would be 11000001. Okay, it would be the binary expansion. I'll write that out here in a little bit, but anyway, that's all I'm saying here. So of course I can always do that. I can do this for any number. This is just saying that a number has a base 2 expansion, so I'm not doing anything crazy here. I can always expect to be able to do this for whatever my exponent is. Okay, so I've done that. And how does this help me? Well, now I can get to the finish line by just multiplying powers of 3 matching this binary expansion. Right, so 3 to the 385, of course, is congruent to 3 to the 256 times 3 to the 128 times 3 to the first. Right. But I've already computed what these things are. That's in my list. So this is congruent to 3 to the 256, that's 326, times 3 to the 128 is 184, times 3 to the first is just 3. So now I have this product of 3 things, and I can actually just compute. So of course there's a number of ways you could do this. Some are quicker than others, but I could just actually compute this product and then reduce mod 479. So this turns out to be 327. Okay, so this is 327 mod 479. And that was exactly what I wanted to figure out. Okay. All right. So that's how that goes. And this example is plenty good. This is actually pretty much the only example you really need to see, because this shows you exactly what goes on when you're doing this process. So you can actually use this to quickly compute these exponential terms, mod m, pretty quickly. So I'll just lay out the general term, and then that's pretty much all I wanted to say about the process, because that's how it goes. Okay. So the process is the following. So how do I do this? Well, the idea is one, compute these successive squarings of A. So what is it that I want to do? I want to compute A to the n. That's congruent to something mod m. Right? So that's what I'm trying to express. Okay, so compute successive squarings of A, stopping when you exceed the exponent m, right? Oh, sorry, I'm using n here. Okay. All right, I've swapped this. The textbook swaps these. It's fine. Second part, right? The exponents binary expansion. So n is equal to something. Let's, so some a sub k 2 to the k plus a sub k minus 1 times 2 to the k minus 1, and so on, all the way down to a sub 1 times 2 to the first plus a naught times 2 to the 0, right? This is my binary expansion. Looks something like that. Okay. This is just me expressing this thing as a sum of powers of 2, right? Okay. And then lastly, multiply together the powers a to the 2 to the, say, j, corresponding to the 1s in the binary expansion of n. Yeah, I should include here that these a sub k's, right, these a sub j's here, they're all either 0 or 1, right? So 0 is less than or equal to a sub j is less than or equal to 1 for all j. So every single one of these a sub j's is either 0 or 1, right? These are integer values, so there's no other value those things can take. Okay. All right. So that's how it goes. So note for step 2, what we really did was to say that 385 base 2 is 1 1 0 0 0 0 0 0 1. That's the same thing as saying that this is 256 plus 128 plus 1, right? So here's the 2 to the 0, first, second, third, fourth, fifth, sixth, seventh, and eighth, right? So here's the 2 to the 0 slot, here's the 2 to the 7th slot, and here's the 2 to the 8th slot. Okay. All right. Now, of course, to compute the binary expansion, you can do that just by just by dividing by 2 a bunch, right? So that's no issue. Okay. So this is our process for computing these exponents, a to the n mod m. Now, we'll talk about that more when we talk about applications later, and there's other expressions and theorems that we're going to state dealing with these exponential terms like this. So this is going to be a recurring thing that we talk about. But for now, that's all I wanted to say. So we will return to that discussion soon enough. But moving on, we can discuss divisibility tests. So you have been taught these at various times in your math education. You've probably been a while since maybe you thought about using a divisibility test unless you just needed it for some quick practical thing. So we're going to talk about all of the standard divisibility tests, so because now we have the terminology to make this discussion a lot more straightforward. So the simplest thing, of course, there's a group of very simple divisibility tests, right? So the first thing is, if you think about divisibility by 2, that's just looking at whether or not the thing is even. And you could say that it's even if its last digit is even, right? So divisibility by 2 is just immediate. So divisibility by 2. So we'll say n is divisible by 2 if its last digit is divisible by 2. Okay, phrased in another way, n is even if its last digit is even, right? Okay. Of course, talking about divisibility, this isn't really just an if, this is an if and only if statement. So n is divisible by 2 if and only if its last digit is divisible by 2. So n's even if and only if its last digit's even. So if its last digit's odd, it's not divisible by 2. So that's something that you haven't really had to think about at all. You've been doing that all your life. Let's take care of all of the really easy ones first. So first is divisibility for 10 and 5, right? So the number n is divisible by 10 if and only if its last digit is 0. And is divisible by 5 if and only if its last digit is 0 or 5. Okay, so we've taken care of divisibility by 2, and we've taken care of, once we prove this proposition, divisibility by 10 and by 5. Okay. All right, so how do I say this? Well, it's one way of proving this. Let's start out with divisibility by 10. Well, note that ten is congruent to 0 mod 10. Thus, 10 to the k is congruent to 0 mod 10 for all k, right? For all integers k. That is a strict inequality. Okay, so let's consider the base 10 expansion of n. So what is that? That's me expressing n as some a sub m 10 to the m plus a sub m minus 1 10 to the m minus 1 and so on, all the way down to a sub 1 times 10 to the first plus a naught times 10 to the 0, of course. But every single one of these terms has a 10 in it except this last one. This last one is just a naught, right, since this is a 1. And so mod 10, this is congruent to a sub m times 0 plus a sub m minus 1 times 0 plus, and so on, all the way out to a sub 1 times 0 plus a naught. And so this is congruent to a naught mod 10. So what did we just do? Well, we just used the base 10 expansion of a number to say if we've written out a positive integer using its normal base 10 form, then mod 10, what is that integer? It's congruent to its last digit, right? Now you might have said, wait a minute, like I noticed something here. So suppose that you had in front of you the base 9 expansion for some number, right? Mod 9, what is that number congruent to? Well, it's congruent to its last digit, mod 9. But when we say last digit, we would mean last digit in its base 9 expansion. Okay. So because naturally, obviously, we use base 10 to express numbers, we don't have to make that distinction when talking about mod 10. But the same is actually true for every modulus that you pick. So if you had basically if you had a list of, if you had a number and you had its base b expansion for like 10 choices of b written out in front of you, you could immediately tell me what that number is mod b for any choice of b by just reading off the last digit of its base b expansion. Okay, that's that is a lot of words to say something that's actually pretty obvious. But anyway, so my number is congruent to a naught mod 10. But if I want this thing to actually be divisible by 10, being divisible by 10 means being congruent to 0 mod 10. So n is divisible by 10 if and only if a naught is congruent to 0 mod 10. But what does that mean? That's if and only if a naught is 0. Why is that? Well, digits in the base 10 expansion are integers that are allowed to be what? they can be 0, but they have to be strictly less than 10, right? So they only go up to 9, right? So for this range of integers from 0 to 9, only one of them is divisible by 10, and it's 0. Okay. So proof for divisibility by 5 is similar. So I'll leave that to you to work out the details. Okay. All right. So that takes care of divisibility by 2, 10, and 5. All right. So I don't doubt, I don't think I doubt your abilities to tell me whether or not a given integer is divisible by 2, 10, or 5. So I won't worry about giving a bunch of examples or anything. Okay. So what's next? Let's do divisibility by 4 and 8. Okay. You might remember these as well. So how do I figure out divisibility by 4 and 8? Well, the integer n is divisible by 4 if and only if its last 2 digits are divisible by 4. Okay. All right. The integer n is divisible by 8 if its last 3 digits are divisible by 8. Now, the thing is that I've chosen to state this in a way that could be kind of confusing here, so maybe I should say what I mean here. When I say its last 2 digits, I don't mean that both of its last 2 digits are divisible by 4, so this seems a little confusing. What I mean is that I take the number formed by its last 2 digits. Okay. And when I say its last 3 digits here, I mean the number formed by its last 3 digits. So that this should hopefully explain any confusion there, because the way that it's stated, it makes it seem like, well, it makes it seem like its last 2 digits would need to be some combination of 4 and 8. Well, 0, 4, and 8 for 4, and 0 and 8 for 8. And that's just not the case. Okay, so this maybe makes it make a little bit more sense. Okay. Now, how to prove this? You might already expect what's going on here. Well, why is this the case? You are correct if you note that, wait a second, I'm realizing now all these divisibility properties, of course, are an artifact of the base 10 number system. And divisibility rules in some other base would, be correspondingly different, right? And that's very much the case, right? We make a ton of references to digits, which obviously is referencing the base 10 expansion with the base 10 place value. So of course that matters. And what is going on here is the fact that 4 I get from a square and 8 I get from a cube, right? That's what's ultimately going to make this the case. So that for 4 I get the last 2 digits, for 8 I get the last 3 digits. What am I saying here? So first, note that if k is greater than or equal to 2, then 10 to the k can be written as 10 squared times 10 to the k minus 2, right? Which is 100, which is 4 times 25 times 10 to the k minus 2, right? Which is congruent to 0 mod 4. It's a multiple of 4. So before I said something that sounded insane, like I got 4 from a square and 8 from a cube. What did I mean by that? I mean 10 squared is 100, which is divisible by 4, but it's not divisible by 8. Okay. The process for 8, we're going to do a similar thing here where I've rewritten 10 to the k as 10 cubed times 10 to the k minus 3. And 10 cubed is now divisible by 8. And so that's the point. Okay. So then how does this work? Thus, writing in using its base 10 expansion, I get a sub m times 10 to the m plus a sub m minus 1 times 10 to the m minus 1. From this fact, you see how this is going to work out, that my last 2 digits form a number, and that number has to be divisible by 4. So going all the way down, this is a sub 1 times 10 plus a naught, right, the ones place. So using this fact, all of these are congruent to 0, so this is congruent to a sub 1 times 10 plus a naught mod 4. Right. Okay. Thus, a number is congruent mod 4 to the number formed by its last 2 digits. So n is congruent mod 4 to the number formed by its last 2 digits. That's the important bit. Thus, this number must be congruent to 0 mod 4, i.e. divisible by 4 for n to be divisible by 4. Okay. And the implication goes both ways. I'm not going to rewrite that, but the implication goes both ways. So if the n I started with was congruent to 0 mod 4, then since it is also congruent to the number formed by its last 2 digits mod 4, The number formed by its last two digits mod 4 is congruent to 0, i.e. divisible by 4. So implication goes in both ways, and we get divisibility by 4. So divisibility by 8 is similar. So to note how this works for 8, 10 to the k is equal to 10 cubed times 10 to the k minus 3, which is 8 times 125 times 10 to the k minus 3 for all k greater than or equal to 3. So that is, of course, congruent to 0 mod 8. Okay. So for k bigger than or equal to 3, 10 to the k is congruent to 0 mod 8. So you're only left with the last 3 digits. And so divisibility by 8 means that that number formed from the last 3 digits has to be divisible by 8, or congruent to 0 mod 8. So that's it. It proceeds in exactly the same way. Okay. So we've got divisibility by 2, 10, 5, 4, and 8. Okay, we're not going to do divisibility rules by 7. 7 is always very annoying here. Okay, but we are going to do the rest up to 11, I think. 11 is where we're going to stop. So the next is divisibility by 3 and 9, which you might remember was some of the more fun. So divisibility by 3 and 9. These were the ones that were slightly more fun than the others. Okay. So a number n is divisible by 3 if the sum of its digits is divisible by 3. And a number n is divisible by 9 if the sum of its digits is divisible by 9. Alternatively, a way of saying this is the following. So this follows from the following fact. So this takes care of divisibility by 3 and divisibility by 9. So there is a fact, an integer mod 3 respectively mod 9 is congruent to the sum of its digits mod 3 respectively mod 9. Okay. So why does this first thing that I wrote follow from this fact? Well, according to this fact, if we'll just use mod 3 as an example. So if we're looking at an integer mod 3, it's congruent to the sum of its digits mod 3. So if the sum of its digits is 0 mod 3, then the integer is 0 mod 3. Being 0 mod 3 means you're divisible by 3. So both the number and the sum of its digits are divisible by 3. Okay, similarly for 9, so this thing that I stated here that I'm boxing in now is a direct corollary of this fact. So really all I need to do is prove the fact. There is actually a really simple proof of this. You may have even seen this before when you first learned about this, just using the expansion. You don't have to use congruences at all. You could have actually done this the second that you were told about base B expansions. You can actually prove this fact. But I'm going to use congruences to do it, and then I'll show you how you could have done it without ever referencing congruences. So note that 10 is congruent to 1 mod 3. Okay. Of course, you might say, well, it's also congruent to 1 mod 9. Yeah, that's true, right? So again, you're thinking to yourself, okay, well, this definitely depends on the number base, right? The fact that we use 10 here and the fact that 9 is 1 less than 10 has something to do with the integer mod 9 being the sum of its digits. In fact, if it's not, I haven't looked yet, but in your next homework, if it's not actually listed as a homework problem, I'll assign this one. In fact, I might give you one that's like a quickie. I might have like a little micro assignment that's like a single problem that'll be due like the next day, maybe. Which is I'm looking through right now. I don't see it immediately, although it's probably here somewhere. It's yeah. Anyway, so what it is the following. It's coming up with some divisibility rules for numbers expressed in base B. The quick one is let's choose any number base you want to, B. Okay. So I have a number in base B. And I want to check for divisibility of that number by b minus 1. So how do I do that? Well, it turns out that mod b minus 1, that number is congruent to the sum of its digits in its base b expansion. Okay? So this is totally, like, once you write it down and once you see what I write here in a second, it's like 100% clear why this is. So there's no mystery here, but it's a little bit interesting to think that, maybe you thought like, oh, there's something like special about the number 9, right? That maybe the first time you learned like multiplication, your times tables, you noticed the pattern, right? Of, okay, well, 9 times 1 is 9, okay, and 9 times 2 is 18, so 1 plus 8, okay, and then 9 times 3 is 27, so 2 plus 7, okay. Probably noticed that pattern the first time you saw it, how you're counting up and down simultaneously in the digits, and if you write, of course, all of them all the way to 9 times 10, you get the nice, it's counting up in one digit and counting down in the other, and it always sums to 9, right? What's funny is that, like I said, you might have thought like, oh, 9 is like a magic number, but really 9 is just 1 less than 10, and 10 is the number base you're using, and that's what's doing it. So So 10 would work in the exact same way if we were in base 11. And in base 300, well, then 299 would be just as special as 9 is. So it's interesting to think about. Anyway, continuing on here. If I note that 10 is congruent to 1 mod 3, then 10 to the k is congruent to 1 to the k, which is congruent to 1 mod 3. And that's for any k. Doesn't matter what it is. Right? Thus, looking at the base 10 expansion, so looking at the base 10 expansion of n, what do I have? N can be written as a sub m times 10 to the m plus a sub m minus 1 times 10 to the m minus 1, and so on, all the way to a sub 1 times 10 plus a naught. But every single one of these powers of 10 I can replace with a 1 mod 3, right? So this is congruent to a sub m plus a sub m minus 1 plus, and so on, all the way to a sub 1 plus a naught mod 3, i.e. it's equal to the sum of its digits mod 3. Okay. Well, mod 9 works in exactly the same way. Once you note that 10 is congruent to 1 mod 9. That's it. Okay. Okay. Well, this is nice. This is particularly useful because this is something that can be very, very quickly computed. Because summing digits, even if the number is like really, really long, summing the digits is something that you can do pretty quickly, right? Okay. So, quick example. Let's see whether or not 9,007. No, that's not 9,789,000. So 9,789,042. Let's see if this is divisible by 3 or by 9. Well, 9 plus 7 plus 8 plus 9 plus 0 plus 4 plus 2. Of course, this is, if I sum all this together, this is 39. So 15, 18, so 33 plus 6, so 39, yeah. So this is 39. That's divisible by 3. So this is divisible by 3 since 39 is divisible by 3. Okay. But it is not divisible by 9. Okay. Not divisible by 9 because 39 is not divisible by 9. Okay. So note, we could have proven this divisibility test. So we could have proven this divisibility test using just the base 10 expansion. So no congruences. I mean, okay, using no congruences, like the little bit of congruences we're using is really just to kind of tidy up the language. So everything I'm doing here that I'm about to do could have been expressed with congruences. But notice that if I write out its base 10 expansion, then what does its base 10 expansion look like? Well, it's a naught plus a1 times 10 plus a sub 2 times 10 squared plus and so on. So what does this look like? Well, I can rewrite this as a naught plus a1 times 1 plus 9 plus a squared times here, instead of splitting this as 1 and 9, I could split this as 1 and 99. And then next, a sub 3 would be 1 plus 999, and so on. So note I can always do this splitting, and these are all divisible by 9 and 3. By both 3 and 9. So, what do I get? I get n is expanding each of these. It's the sum of its digits. Right, plus something times something divisible by 9, by 3 and 9. Something divisible by 3 and 9. And this is the sum of the digits of n. So this is a totally elementary, like totally intuitive way of proving this same fact. The idea is just looking at the base 10 expansion, you could do this trick where you split off 1 from each of these things. Splitting off 1, what you're left with is a thing that's divisible by both 3 and 9. As I said here, you can do this for any number base. So in base b, you can do this for b minus 1, and it works out just fine. Okay. Okay. So that's another way we could have proven this. There's a fun trick. I'm not going to go over. If you want to look at it, it's at the top of page. Neat mental math trick. Not a trick for computing. It's like a trick, like a parlor trick for your friends. So neat mental math trick, page 128. It actually begins on the previous page, but so page 128 has a neat mental math trick you can do, having someone pick like a 5-digit number, and then like tell you what the 5-digit number is, say that it's random, then have them square it using a computer or calculator or whatever, and then have them read off the digits to you in any order, and then you can have them leave out one of the digits basically, and then you can quickly, in like 10 seconds you can figure out what the missing digit is. So and you're doing this just with basic congruences and using this fact that mod 9, the thing that the integer in question is congruent to the sum of its digits. Okay, so one more divisibility rule is the one for 11. So one more proposition And this is divisibility by 11. Okay, well, an integer mod 11 is congruent to the alternating sum of its digits starting with the ones place. That's A naught. Okay, subtracting the tens place. That's A sub 1. And so on. Thus, n, which I'm going to write its base 10 expansion in the usual way, is congruent. This is congruent to A naught minus A1 plus A2 minus A sub 3 plus and so on, all the way up to plus minus 1 to the m, A sub m mod 11. Now, you probably understand exactly exactly what's going on here. I can think of 10 as being 11 minus 1, right? So, the last thing I want to say before I actually write the proof. Thus, n is divisible by 11 if and only if the alternating sum of its digits is divisible by 11. You might notice that for the really easy things, right, like when you're first learning your multiplication tables, right, 11 was really easy because, well, it's 11, 22, 33, 44, 55. It's repetitions. So using this divisibility rule, what does that say? Well, for 11, 1 minus 1 is 0. That's divisible by 11. For 22, 2 minus 2 is 0. That's divisible by 11. For 77, 7 minus 7 is 0. So that's divisible by 11, and so on. So it's trivially the case for those, of course. But this is going to work regardless of what the number is. And again, as I was saying before, this really has to do with the fact that we're using base 10 and 11 is 1 more than 10, i.e. 11 minus 1 is equal to 10. That's what does it. So the proof is the following. 10 is congruent to minus 1 mod 11. Okay. Again, you don't have to do this with congruences. You could have done it without, although you would have to make an argument, using you could make an argument using the binomial theorem. But I'm not going to get into that. So with congruences, this is a lot easier. So 10 is congruent to minus 1 mod 11. So then 10 to the k is congruent to minus 1 to the k mod 11. So n is congruent to literally the alternating sum here, right? Replace every single one of these with its alternating sum. Starting with 0, of course, I'm going to get positive 1, so it's exactly the thing in question. And I'm done immediately, because since n is congruent to this thing mod 11, I am asking a question of when n is congruent to 0 mod 11, and that's true when that alternating sum of its digits is congruent to 0 mod 11, i.e. is divisible by 11. So that's it. Okay. So congruences actually make it really easy to prove all of those facts that you've been familiar with for a while. Again, a lot of them you can do without congruences. It's a little bit messier for some of them, but for most of them you can actually do it without congruences. But congruences makes it tidier, makes it a lot easier to deal with. Okay, so the next thing, which is probably this and the Chinese remainder theorem, are kind of like the main things that we're going to deal with congruences for now. So the first is talking about linear congruences. And we're going to see how these are related to linear Diophantine equations that we dealt with in chapter 3. Okay. So what is the idea? What do I mean when I say linear congruences? I mean I want to solve the congruence AX is congruent to B mod M, where A, B, and M are given, and X is the thing that I'm solving for, right? So some examples, say 3X is congruent to 4 mod 7. Okay. So you think, I already know some things that I can do if I want to talk about dividing, but of course, remember that it's a little iffy when I can't just straight up divide by 3 here, because 4/3, that's not an integer, right? And I'm just ignoring of the, the rules of when I can divide by something. Dividing by 3 here is not something I'm going to do. So I think, what do? I could just randomly shot in the dark make guesses, right? So I could just try different values of X until I actually get something that works. So I just guess or try different values of X. I find that X equals 6 works. So note 3 times 6 is 18, which is indeed congruent to 4 mod 7. Right. Okay, so that works. Okay, but obviously this just blindly trying values, that's never a thing that we want to be doing ideally. And so it's not clear what I should do in a case like this, right? What if I had another equation? So let's say 3x equals 6 mod 12. Okay. So I can divide by 3, which takes me out of the mod 12 world, and then I can go back to the mod 12 world by being careful with the solutions that I find. So it turns out that solutions are X is congruent to 2, 6, and 10 mod 12. Okay. One more example is 2x is congruent to 1 mod 4, we'll say. Well, this has no solutions. Why? Think about what this expression says. So whatever x I pick, I'm multiplying it by 2, right? Well, that's always even. So mod 4, an even number only has 2 options. It's either congruent to 0 mod 4 or congruent to 2 mod 4, right? If you take an even number and you divide it by 4, the only options for remainder are 0, in which case it's divisible by 4, or 2, in which case it's even, but it's not divisible by 4, right? So its remainder has to be 2. That's the only option. If its remainder was 1 or 3, then you could write it as an odd number, and that's impossible. So no solutions. Note 2x is congruent to 0 or 2 mod 4, regardless of what x is. Okay. Okay. So we see that these linear congruence equations I'm trying to solve, there's a lot of options here. I can have, well, the question is this the only solution? Here I have multiple solutions I've already found, and here I have no solutions, right? So I have a range of options here. So it turns out there's a major theorem that relies on our theorem 3.1 from chapter 3 that's going to tell us exactly how these linear congruence relations go. So big theorem. This is called 6.18 in the textbook. This is, I'm not going to give it a name, I'm just going to say what it does. So this is solving linear congruences. Okay. So what does this say? So let m be a positive integer. Okay. And let a be non-zero. Then the congruence a times x is congruent to b mod m has a solution if and only if d, which is the GCD of a and m, is a divisor of b. If this is the case, that is, if d divides b, then there are exactly d solutions. So the GCD itself gives the number of solutions that are distinct mod m. All right. That is something that we have to worry about. That's something we have to make sure that we say, because of course when you're doing congruences, right, there's infinitely many representatives you could have chosen, right? So when we say distinct, we mean distinct mod m, not that you can use a different number to express them, but technically it's the same thing, mod m. So these are distinct mod m. Okay, so in this case, if x naught is a solution, that is, x naught is any solution, x naught is a particular solution. So if x naught is a solution, then the solutions mod m must be of the form x equals x naught plus m over d times k for some k that is less than or greater than or equal to 0, but strictly less than d. Okay. And the solution x naught This is actually going to tell you how to find this particular solution, because we're told that the general form of the solution, right? The general solution is of this form, but the solution x naught can be taken to be any integer satisfying the following congruence. This is a over d. X naught is congruent to b over d mod m over d. Okay, so this says a lot. All right, this theorem is kind of a long and winding statement. Okay, but I'll stop for now since I'm out of time, and we'll start with the proof of this theorem tomorrow. So I'll show the statement of the theorem, I'll talk about what it's actually saying, and then I'll prove this theorem, go on to the Chinese remainder theorem, and finish proving that tomorrow, and then we'll be done with chapter 6. We'll be moving on from there. So your exam should be graded hopefully within the next few days. So you should get notifications in Elms, when that's ready. And like I said, I'll post solutions to your exam later in the week. So that's that. I'll see you all back here tomorrow. Like I said, we'll finish out chapter 6.